Okay, friends, let's stop making these distributions by hand and let's focus on the more important parts of them, which is the overall shape of the distribution and honestly the average, and if we need it, the standard deviation. So I've built another tab into our Excel calculator. If you go ahead and crack that thing open, we've already explored the stats raw data and the stats group data. The binomial is so important, I decided it probably needs its own tab. So if you click over to that binomial distribution tab, it's going to look a little bit much at first. So we're gonna kind of tackle this thing one piece at a time. So what I'm going to do is I'm going to use it to show you how it creates the distributions for some of the various examples we looked at today. For example, a couple of videos ago, I said, what if you roll 5 dice, or roll a die 5 times, I guess, and keep track of how many 3s that you got. So you pick a die up, roll it again, roll it again, roll it again, roll it again. How many 3s do you get? Keep track of it. You can visualize that by looking at the distribution. So what you're going to do first is you're going to fill out 3 boxes, this box, and this box, and the sheet will take care of the rest. So as far as the smallest and largest x's go, looking at that first, you just have to read the situation. If you're going to roll a die 5 times and keep track of how many 3s there are, well, the least number of 3s that you're going to have is 0, and the most number of 3s you're going to have is 5, because you could roll 3 5 times in a row. It's totally possible. So if I press enter, it's going to adjust. Now this is not quite right, because the binomial probability that I've got up there is 75%. And you know, and I know, that if you roll a die, the chance of getting a 3 is not 75%, it's 1 in 6. So I'm going to type that in here, and I'm going to type it as equals 1 divided by 6 to get all the decimals that I'm allowed to by Excel's float point. And there we go. It's about 16.7%. And when you look at this, this is what's kind of interesting about it. You look at the distribution and look at that mathematically. The chance of getting no 3s out of 5 is the same as the chance of getting 1 3 out of 5. That's pretty cool. Okay, I know we just got done saying, let the Excel calculator run the probabilities for you, but that's just too cool. I wasn't expecting that. I didn't really think deeply enough about it to show that the probability of 0 3s out of 5 is the same as probably 1 3 out of 5, and I just wanted to stop for just a moment and figure out why. So the chance of no 3s, if you roll a die 5 times, means that you have to roll everything else each time, or one of everything else each time. So that means there's a 5/6 shot each time of not getting a 3. So that is going to be 5/6 to the 5th power, right? 5/6 times 5/6 times 5/6 times 5/6 times 5/6, which I'm guessing is that 40.19% that we're getting there. What's the chance that you get exactly 1 3? That looks terrible. 1 3. Well, this is where the binomiality comes in, because 1 3 means you got a 3, which is going to happen 1/6 at a time, and that means you also have to get 4 5/6, right? And you might look at that and go, Sean, those aren't the same thing. And you're right, they're not the same thing at all. But that's because we're forgetting something, the binomial coefficient. Because if you roll a die 5 times, where can the 3 be? Well, it might be on the first roll, or the second roll, or the third roll, or the fourth roll, or the 5th roll. So you'd have to multiply this whole thing by 5, because that's the total number of ways that the 3 could appear in all the different places. And then when you look at it mathematically, oh yeah, 5 times 1/6 is 5/6, and then this over here is 4 more 5/6. So when you multiply it all together, it ends up being the same thing as the previous one. So that's pretty cool. That's a nice little random happenstance that I wasn't planning on. So I'm glad I picked the number 5 randomly to roll a die. All right, let's get back to the Excel calculator. Now that's one of those things that I personally wasn't thinking about when I created this problem. And what's so cool about this too is you can then say, well, does that continue if I roll a die, say 6 times? And if you just change this to 6, it changes the distribution to 6 dice. And you can see you get a really nice graph. Let's go back to the 5 case for a second. you get a really nice embedded graph. It's got all the random variable possibilities here. You've got the stacks over here. If you want, you can even add the data labels if you want. It'll put the probabilities up there. If you want, that's up to you. Let's look at the chicken example that we led this off with, which was my chicken flock. You're going to buy 4 birds and keep track of the girls. And remember, the girls have a 90% chance of being female from a pullet. That's what the graph of that distribution looks like. And that's what the distribution looks like. And those numbers over there on the left should look familiar to you because we came up with those on the board, right? Those are the exact same numbers we got. This is a super, super handy tool because it generates a number of things. First of all, it generates the distribution. Let's go back to Mike's because I like Mike's. That's the one that I just had in that last video. It generates, as we said, the t-table that we spent quite a bit of time recently building by hand. It also generates a graph of that t-table. If you want to make this graph a little bit more specific, you can actually click up in this cell up here and type x equals number of girls. And when you strike enter, it'll actually carry that label right down there for you. So that's just something I built into the spreadsheet. I figured I'd leave probability of x as p of x because that's what you're graphing. That's the whole point of this distribution, is to get those probabilities. Okay, but there's something else that's super important that you're getting. I shouldn't say super important. It might be super important in certain applications. It's right here in these cells right here. You see the Greek letter for mu and the Greek letter for lowercase sigma. And you haven't seen those in a while because we haven't been talking about those for a while because those are the population average and the population standard deviation. And we haven't been talking about that because we have not had populations for a while. We have been dealing with samples. But here's the deal. Assuming a probability of 90% and assuming we're buying 7 birds, this is exactly what will happen in the population if we draw 7 birds. So that's why we can call it mu. Am I going to get upset if you call it X bar? No. Am I going to yell at you if you call it the average? No, because that's what it is. But you're allowed, if you will, to call it mu. Just like you're allowed to call that little one sigma. Now, the calculator, as you're playing with right now, is really to get the distribution simply. Believe it or not, the average and the standard deviation of a binomial are incredibly simple formulas. Let's take a look at those right now. The average can be found really, really simply by taking the number of trials, which in this case is 7, and multiplying it by the binomial probability of 0.9. So 7 times 0.9 gives you 6.3, which you see right there. The standard deviation is a little more devious. It's got a really fun formula. It's a square root of n times p times 1 minus p. And if you run these numbers through that, you take 7 times 0.9 times 0.1, multiply all that together, and then take the square root of it, you're going to get 0.794. I don't expect anybody in here to memorize those formulas, but if you are interested in those formulas, I've got links in this video's comments section or somewhere down there in the information box to some documents where I've proven why those formulas work through the lens of probability distributions in general. If you want to geek out or if you're having a hard time sleeping sometime, take a look at those. I'll put you right out. So what's just so cool about this sheet is you just have to feed in the situations. Remember on the first day of class videos I watched, I flipped 10 pennies. Remember that? So I took 10 pennies, which have a probability of 0.5, and that hopefully should not surprise you absolutely one bit. That looks like a perfectly balanced bell curve left to right. Because as you've noticed, if the pennies are slightly skewed like that, or like that, or like that, the shape of the curve is going to change quite a bit. You can also move it over to the other side. There's all kinds of ways you can mess with this curve. And what's so nice about this is it allows you to goof around with the probabilities without having to worry about all that mucky muck of figuring out those coefficients and all those individual row level probabilities. Now I'd like to share another question with you. Taking a trip back in time, summer of 2010. Here are some pictures I took of our son walking around in the summer of 2010. That was a long time ago. But as he walked around that summer, what did I observe? What could I have possibly been interested in to talk about this in a stat class, in a Math 243 class? If you're interested, I'm going to wrap that up in the last question of your homework. Okay, so that's really all we have to talk about as far as the binomial goes. We've ticked all the boxes that we have to worry about. The next video after this is completely optional if you want to take a deeper dive into where those coefficients came from. So watch it if you want, otherwise jump to the homework.